So is there a systematic difference between the scores in the first treatment condition and those in the second treatment condition? The hypothesis test uses the difference scores to obtain an overall mean difference for the entire population. The null hypothesis says there is no systematic difference between the treatment conditions, and the alternative hypothesis says there is a systematic difference. The hypothesis test helps us decide between the two alternatives. As before, the numerator measures the actual difference between the data and the null hypothesis, and the denominator measures the standard difference that would be expected if the null hypothesis were true. Big T values, as before, means we can reject a null hypothesis, as the means are far away from the population mean and what would be expected if there were no treatment effect. So they are highly unlikely to have been obtained by chance alone. Let's look at an example. Research indicates that the color red increases men's attraction to women. So a test photograph was mounted both on a red cardboard background and a white cardboard background and was presented to men in a stack of many photographs. And the men rated the attractiveness of each photograph on a 12-point scale. Of course, what we're interested in is the difference in the test woman's rating by the men when she's presented on the red background versus the white background. Here you see the statement of the null and the alternative hypotheses. The null saying that there will be no difference in her attractiveness ratings regardless of the color background, and the alternative saying that there will be a difference. Participants in this experiment were n equals 9 men. So to get started with our hypothesis test, we need to calculate the degrees of freedom, which is of course n minus 1, giving us 8 degrees of freedom. And with an alpha level of 0.01, we can take this critical value to our t-table and find the two-tailed value is 3.355. Here is what our distribution looks like with 8 degrees of freedom and an alpha level of 0.01. So if we find a mean difference greater than 3.355 or less than negative 3.355, we shall reject the null hypothesis and conclude that there is in fact a difference in the attractiveness ratings depending upon which color background the test woman's photograph was presented on. But if we find a mean difference in the white area of the distribution, we will fail to reject the null hypothesis and conclude that there is no evidence that the color of the background matters. And so here is our data table of the attractiveness ratings that the men gave to the test woman's photograph. The participants are listed in the column labeled by letters A through I, and their ratings for the test woman's attractiveness on both the white background and the red background are also listed here. You'll see that we have calculated a difference score, that is the red background minus the white background rating, giving us those values. So for participant A, 9 minus 6 equals a positive 3. For participant B, 9 minus 8 is a positive 1, etc. Also, you'll notice that if we add up the D values, we get the sum of D, which we're going to need to calculate the mean difference. And also we have added a D squared column and a sum of D squared, which will be necessary for calculating the sum of squares. In this case, the sum of squares is not given. Of course, the D squared values are just the D values squared. So for participant A, 3 squared equals 9. For participant B, 1 squared equals 1. For participant C, 3 squared equals 9, etc. And then the sum of D squared values are, of course, just the D squared values added up. On the bottom of the slide, we begin the calculations necessary for this hypothesis test. First, calculating the mean difference, which is the sum of D divided by the N. So in this case, we calculated sum of D to be 27. The N is 9, or the number of participants, giving us a mean difference of 3. This number will, of course, be the representation of our data in the T statistic. We also need the sum of squares value, though, to get the variance estimate, and the calculation for that is Here, it's, as you may recall, sum of d squared minus the sum of d's squared over n. So we have all of those numbers here to do the substitution. The sum of d squared is 99, stick that in, minus the sum of d's, that's 27 squared divided by the n is 9. So that gives us 99 minus 81, or a sum of squares equaling 18. Take a moment and make sure you understand how to get these values. We needed that sum of squares value, of course, to get the variance, or the s squared value. That is given by sum of squares divided by n minus 1, or in our case, 18 divided by 9 minus 1, or 8. So our variance is 2.25. The sample variance that we just calculated gets plugged into our calculation for the estimated standard error, which is the square root of s squared divided by n, or in our case, the square root of 2.25 divided by 9, that is s squared over n. And when you complete the algebra, you get an estimated standard error of 0.5. This will, of course, be the denominator in our t equation. And now we can work through the substitution of the t equation. Of course, that is the mean difference, that's the value from the sample, minus the mu difference, that is the population parameter hypothesized by the null hypothesis, divided by the estimated standard error. So our mean difference was 3, minus that value predicted by the null hypothesis, which is 0, divided by the estimated standard error, which we just calculated to be 0.5. So that gives us a t value of 6. Make sure you understand these calculations before you go on. And when we compare that t value of 6 to our distribution that we drew, we can see that it is far in the tail of the high end of distribution, so we will reject the null hypothesis.
And here I have added the formal statement of these results. That is a t with a degrees of freedom of 8 equals 6. The probability of obtaining this result was less than 0.01, so we shall reject the null hypothesis. What this means, practically speaking, is that a woman is rated by men as statistically significantly more attractive when she is presented on a red as opposed to a white background. So this seems to suggest, ladies, if you don't already have a red sweater, you might want to buy one.
Here are the calculations for the effect size measures, Cohen's d, and the percentage of variance accounted for, as well as the statement of the confidence interval for the related samples. There is nothing different about the logic, nothing different about the calculation at all. Just take a second to familiarize yourself with the new notation. For Cohen's d, we will use the mean difference divided by the standard deviation. So that is 3 divided by the square root of the variance. Remember, the s squared was 2.25, so to get the s, we need to take the square root of it. So 3 divided by the square root of 2.25 gives us an estimated Cohen's d of 2, which, as you'll recall, is a quite ginormous effect size. The calculation for the r squared is t squared divided by t squared plus the degrees of freedom, as it's always been. Our t was 6, so that becomes 6 squared divided by 6 squared plus our degrees of freedom, which was 8. And when you do the algebra, you get 0.818, which is a quite impressive 81.8% of the variance is accounted for by the color of the background on which the women's photograph was presented. That is literally as big of an effect size as I've ever seen, and the reason that that is possible is because of the added strength associated with the repeated measures designs. Remember, there is no individual difference, variance mucking up the math, so to speak. All of the difference, for the most part, is accounted for by the treatment effect, and that is the presentation background color. And now I've added the calculation for the confidence interval at the 99% level. So that is a t value of 0.01, which with 8 degrees of freedom gives us a t value of 3.355. That happens to be the alpha level that we used for the overall hypothesis test, but remember, of course, we could choose any confidence interval value that we wanted. It just so happens that in this case I did choose the 99% confidence interval, and so when you do the substitution, our mean difference was 3. That t value that we found for the 99% confidence interval with the degrees of freedom of 8 is 3.355 times the estimated standard error, which was 0.5. And so when you do the lower boundary, that is 3 minus 3.355 times 0.5, you get a value of 1.3221 for the lower boundary. And when you do the upper end, that is 3 plus 3.355 times 0.5, you get a value of 4.6755 for the upper boundary. So what this means is that whatever the effect of the difference in background is on the men's attractiveness rating, I am 99% confident that it increases the attractiveness ratings from white to red somewhere between 1.3221 points on a 12-point scale and 4.6755 points on the same 12-point scale. When you report this information in a scientific write-up, or if you're trying to read a journal article, you should expect to see the means and standard deviation in a table, sometimes too in the text as well, and a concise version of the hypothesis test results. That includes the t-value with the degrees of freedom in parentheses, the t-value that obtained, the significance level, and the effect size, as you see in the example below. This slide is entirely review at this point, but it bears mention again, I think. There are a number of factors that influence the outcome of a hypothesis test. One, of course, is the size of the sample mean difference. So the larger the difference between the two treatments, that is going to generate a larger numerator in your t equation, and of course increases your t-value and your likelihood of rejecting the null hypothesis. This, I think, is unsurprising. The bigger the difference, the easier it is to reject a null hypothesis. The sample size, as you know, also increases your ability to reject a null hypothesis by reducing the size of the standard error and therefore the size of the denominator in the t equation. So as sample size increases, the standard error decreases and the t-value will increase. We've talked about that before. And of course, last but not least, as variance increases, the standard error in the denominator of the t equation increases, and so the t-value itself becomes smaller and therefore harder to reject a null hypothesis. One way to look at it is that variability and consistency have an inverse relationship. So when variability is high, consistency is low, and vice versa. When the treatment has a consistent effect, the different scores all cluster together and the variability is low. However, when the treatment effect is inconsistent, the different scores may be scattered all over the horizon and the variability will be high. The consequence of this, of course, is that the treatment effect may be statistically significant when variability is low, but the very same treatment effect might not be significant when variability is high. So consistency in this case will help you reject a null hypothesis. Let's look at a picture of what I'm talking about. Here are a group of different scores with a mean difference of -2. You'll notice the standard deviation is 2 in this case. The variability is low, so the consistency is pretty high. And you can see that the different scores are clustered together and that they are pretty close together and that they are consistently less than would be predicted by the null hypothesis. So in this case, you do have a statistically significant finding. However, on this slide, you have a somewhat different situation. The mean difference is still -2. However, the consistency is very low in this case. The standard deviation is 6. It's 3 times larger than it was before. And so you'll see that the scores, the different scores, are scattered all over the place, and it's much more difficult to see the treatment effect. In this case, the same mean difference, the same magnitude of difference, is now not statistically significant because of the lack of consistency of the different scores and the increase in variance. As is always the case, it is of course possible with a repeated measures t-test to use a directional or a one-tailed test. And so in any instances in which researchers have a specific prediction for the direction of effect, you may want to do this. So we believed that the red background would in fact increase the subjective ratings of attractiveness. And so we could have used a one-tailed test in this scenario. The null hypothesis, if we had, would have been phrased as the mean difference will be less than or equal to 0. And to make sure that the two hypotheses are mutually exclusive and cover all logical ground, the alternative hypothesis would then be phrased as the mean difference will be greater than 0. And of course, the critical region would be located in one tail if we went this route. At this point in our discussion, I would like to get to the final topic that we're going to cover, which is a comparison really of related samples versus independent samples t-tests, and a bit of a discussion about which type should be used under which circumstances. The advantages of a repeated measures design are pretty considerable, really. It requires fewer subjects. We can look at the changes over time. So for instance, seeing how an individual treatment will impact a person over time is an incredibly useful outcome, which there's no other way to achieve. Also notable is the fact that the repeated measures design reduces or potentially eliminates the influences of individual differences, and so there's substantially less variability in the scores. That is, the variability that is there is attributable to the treatment effect or a few other things, but the largest source of extraneous variability is individual differences or the differences among people, and that is largely removed in the repeated measures designs. But the repeated measures design is not perfect. It has some notable disadvantages that have to be accounted for. One pertains to the passage of time. So factors beside the treatment effect may cause the subject's score to change during the time between the two measurements, and that is variance which has to be accounted for. Second, related is the fact that participation in the first treatment may in some way influence the person's score in the second treatment, and this is called an order effect. And either way, these produce variance that has to be dealt with in some way because they will negatively impact your hypothesis test. The standard way of dealing with it is a strategy called counterbalancing. And what counterbalancing is a way to make sure that those differences affect each condition equally. So whatever the difference is, it doesn't have undue effect on the second condition. The way it's accomplished is by taking your group of participants and dividing them in half. The first half would receive condition A and then condition B, whereas the second half would receive condition B first and then condition A. So whatever the order effect or the passage of time effect is, it would not affect only condition B, but it would affect both conditions equally. To me, this all becomes a lot more tangible when you look at actual data. So I've included an independent measures study. It has 2 separate samples with 3 people participating in treatment 1 and 3 different people participating in treatment 2. And on the right side of the slide, I've included a repeated measures study. It has the same 3 people participating in both treatment 1 and treatment 2. You'll notice that for purposes of the example, the scores in treatment 1 in the independent measures and the repeated measures are identical, as are the scores for treatment 2 in both designs. So the numbers are identical in each treatment regardless of the design. This, of course, results in the same 5-point difference between treatment 1 and treatment 2, whether it's the independent measures or the repeated measures study. So all the numbers are the same, but there are some important differences in terms of variability. They have the same scores, the same 5-point mean difference, but the independent measures design allows for the possibility of individual differences to have influenced the treatment effect. In the repeated measures design, however, there's no possibility that the subjects differ from treatment to treatment, and therefore the variability cannot affect the overall sum of squares. The variance is hugely different as a result, affecting the standard error. For the independent measures, you calculate the sum of squares and the variance for each of the samples, and in treatment 1 you'll see that the difference between Bill and John is significant. So the standard error is big, the t-value is small, and you can't reject the null hypothesis. But in the repeated measures study, the sum of squares and variance are computed based on the difference scores. So the big difference is eliminated. That is, the difference between those 2 individuals appears in both treatment 1 and treatment 2, and so it does not affect the difference scores and does not affect the variability. As a result, the standard error is reduced and the t is larger, so you can reject the null hypothesis. This is just a way to see the big advantage of a repeated measures study, and that is it removes the variability associated with individual differences, which gives you a better shot at rejecting the null hypothesis. Like any hypothesis test, there are assumptions which must be met before the related measures t-test is viable. Those are, of course, that the observations within each treatment condition must be independent. That is, you don't want to have siblings or identical twins or married partners in the same treatment condition. They need to be randomly selected. Of course, the observations between the treatment conditions are not going to be independent because it's going to be the same people measured multiple times. But the observations inside of each treatment condition must be independent. Also, the population of difference scores must be normally distributed. This is more theoretical than literal in almost all cases. If you're worried about it, we just need to have larger sample sizes. So n equal to or greater than 30 should alleviate this concern. As we're finishing up this chapter, let's do a couple learning check questions. Assuming that the sample mean difference remains the same, which of the following sets of data is most likely to produce a statistically significant t-statistic? Sure, the answer to this one is C. N equals 30 and sum of squares equals 10. In any situation, a large n and a small measure of variance gives you the best shot at rejecting that null hypothesis. Next one. Compared to the independent measures designs, repeated measures studies reduce the variance by removing individual differences. True or false? That one is true, of course. Using the same subjects in both treatments removes the possibility of individual differences affecting those treatments differentially. That is the principal advantage of the repeated measures design. Last one in this chapter. The repeated measures t-statistic can be used with either a repeated measures or a matched subjects design. True or false? That one's true. Both repeated and matched subjects are examples of related samples tests. Both of these reduce individual differences across treatments, and both of these are mathematically equivalent. And this concludes our discussion of Chapter 11, guys. Good job. Remember, you've got Test 3 and Quiz 11 out there during this module. The big task, I think, in test 3 is, as we've discussed, to sort out which one of the t-test designs you're being asked about and to figure out how to bridge the gap between the information that you're given in the question and the information that you need to solve it. That is, how to get from the starting point to the end point of the solution. And to deal with both of these issues, I've given you that roadmap handout, which I really think you need to spend some time annotating to make sure that it is everything that you need it to be to help you not get confused about the notation or the equations or the interpretation. Should you need any help at all, please just post a note in the discussion board and I will be right there to help get you sorted out. Good luck, and I'll talk to you soon.